If a polynomial f of x over the real numbers has the complex numbers 2 plus I and 1 minus I as roots, then f of x could be one of these several options. So of course, one way of doing this is to simply substitute these two complex numbers into f of x and evaluate and see if we get 0. It seems like that's probably not the most efficient way of doing it. My other thought for an approach is to take the complex conjugates of these numbers. And I mean, if the polynomial f has real coefficients, and if these two complex numbers are roots, then their complex conjugates must also be roots. So what we could do is find the minimal polynomial that has those four numbers as roots. It's easy to write that down. It's just a question then of expanding it and see if we get one of these. Now, is there something we can say about, so like options C and D are certainly ruled out because this thing has to be at least fourth degree. Is there something we can say about even and odd coefficients of polynomials that come like this? I'm not completely sure if there's a result about that. So the other three options, A, B, and E, are all fourth degree polynomials. And so if I write down this polynomial with these four roots and expand it, I have to get one of A, B, or E. So maybe that's the easiest way to do it. It shouldn't be a terribly complicated. Oh, you know what'll be easier actually maybe is to write out, I'll do it like this. I know f is going to be the product of two polynomials. So f has to be the product of p and q, like this. Well, I mean, it could be a scalar multiple of this, or there could be other roots, right? It doesn't say that f is the minimal polynomial. But yeah, I think I'm just going to expand these things and see what I end up getting. This is what I end up getting for f, which is one of the options. It's option C. F doesn't have to be this polynomial, but it could be. It could be f. This is the minimal polynomial that f could possibly be. But yeah, there's not a huge amount more to this. I don't know if there's some kind of shorter way of doing this by understanding properties between complex roots of a polynomial and the coefficients. Maybe there's something that could be applied to do this a little bit quicker. But knowing that f has to at least contain these four terms as factors was pretty much the thing that allowed me to figure this out. And then it's just a question of multiplying these four things together and seeing what f possibly could be. And I'm lucky that this is one of the options, right? If f was a higher order polynomial, then this approach wouldn't necessarily allow us to identify which of these results. And in that case, I would probably just boil down to substituting in each of these roots into all the options and seeing which one comes out as having both of those roots. If I have more to say about this one, I'll put it down in the description. Thanks for watching.